All right. Good afternoon, everyone. I'm delighted to have the opportunity to present an overview of what we're going to try and do with LSST and ESO facilities and worldwide facilities in, let's say, the next decade. So I'm going to talk about supernovae. I was going to call it only supernovae, but it's kind of related transients, since I know a lot of people here work on things that aren't quite. They might be mergers. We don't call them supernovae like kilonovae. And so I'll try and touch briefly on some of the other related topics to supernovae in this talk. So to start, why are we interested in understanding extragalactic transients in the universe? There are a couple of different reasons. Well, they're interesting they're just fun, exciting transients because they explode. But there are loads of different things we want to try and understand within them. So binary star evolution, how do stars end their lives? Do they collide? Do they lose a lot of mass prior to explosion? How does this occur? And then how do different types of white dwarfs merge, white dwarf neutron stars? We want to understand all of that. It's also really important to understand all types of transients because of the nucleosynthesis that they produce. So these transients, we know, produce the heavy elements that we see around us on Earth. A lot of iron is produced in type 1a supernovae, about half solar mass per event. And then we've recently seen evidence in our kilonovae events that these produce our process elements, so rapid neutron capture, and so things like gold and platinum are formed in these events. And then finally, the other thing that I'm going to cover today that we want to do with extragalactic transients is cosmology. And so type 1a supernovae are probably one of the most mature probes of the cosmological parameters. I'm showing here the dark energy equation of state against omega matter. So these are recent results from the dark energy survey, and they put some of the tightest constraints on these cosmological parameters. Okay, so I'm going to start and give just a brief overview of kind of where we stand with the current state of the art in transient surveys, and what are the big, then I'll move on to like what are the things that we could hope to do with LSST. So these are the main telescopes that run extragalactic transient surveys. I know they also do galactic surveys as part of their missions, but these are the main ones that people in this room are a part of and discovering transients from different locations. And so the key here is that we find these transients, and then in most cases to date, we've wanted to get a spectrum of the interesting ones. So if this is the flux of your event, your supernova here, it peaks at say 2 weeks for type 1a after explosion. We want to try and get observations in these first days. And the reason for this is it turns out a lot of the interesting physics on the mass loss and on progenitor companions for type 1a supernovae, a lot of that can be probed by looking in these first days after explosion. So this has been a really key area in recent years. And so just to show some of the different science that you can get out of these very early observations of very rapid spectroscopy. So this is showing some spectra of a core collapse supernova, a type 2b. So the explosion of a massive star. And so the key development here was these narrow emission lines that are signatures of interaction. And so if you see the timestamps here, this first spectrum is 15.5 hours after the explosion. And then this feature here, so H alpha, decays very rapidly at 6 days, it's gone. This is just highlighting that you really have to get the spectra very quickly if you want to try and understand these mass loss events. It's also true for kilonovae. So this is showing the lovely X-shooter spectra that were obtained of 17 GFO, again at different phases. And here it's compared to some modelling that can be used to constrain the nucleosynthetic yields. So again, rapid spectroscopy was key for constraining these properties. And then I just wanted to say as well that we've also moved into much larger population studies of transients as well. So this is very nice work by Dan Purley from the Zwicky Transient Facility. So this is the Bright Transient Survey. So it was a magnitude limited survey of nearby transients. So there's a lot going on in this, but essentially start here and you break it into 1A or core collapse, and then you can break it down into the different subtypes. And so this breaks down hydrogen rich, hydrogen poor. And so this gives you a kind of overview or census of the different types of explosions that we're seeing. And so we're now at 1,200 events that have been put into this sample. So that's the kind of order of magnitude that we're looking at. And I'm also interested myself in white dwarf explosions. So this is a plot that I'll show another one of, a similar one later. So this is the absolute peak magnitude, and then some version of time scale for the transient. So here it's how much it decays in 15 days post-peak. So you have slower declining things here and faster things here. So in ZTF, the normal 1As, they roughly lie here. So they're these grey objects. But what we found in the last few years, and other surveys have as well, that there's this huge diversity in transients that we are fairly confident come from white dwarfs, but they have a huge range of magnitudes, and they also have a very large range in decline rate after peak. And so there's a huge range here, but we think they all come from white dwarfs, and so we have to try and explain that. And so to try and understand some of these fainter ones, you have to link them with fairly exotic sounding models. So it can be disruption by an intermediate mass black hole. And there are models for these. I'm not saying any of these particular classes do match with these, but these are some of the models that have been put forward for different parameter spaces. You can have double white dwarf disruptions, and you can have white dwarf neutron star mergers. So different groups are predicting different values for what these should look like. And so one of the key things now is to try and combine this with the observations. And then on the supernova cosmology side, so as I mentioned, the Dark Energy Survey had their 5-year results right a couple of weeks ago. And so this is the Hubble diagram showing the new DES supernovae, 1,600 of them at these higher redshifts, so shown here in blue. And so one of the key differences with this sample compared to, let's say, traditional supernova cosmology is that they did photometric classification for the supernovae. So just classifying based on their light curve shape, they were able to distinguish between these events and non-type 1a supernovae. So before this, we would always get a spectrum of each event, even at higher redshift, and it's very time consuming. But now these photometric classifiers actually work really well. The other key thing that you do need, or at least it hasn't been proven that you don't yet, is a spectroscopic redshift for each of the supernovae. So what is LSST going to do differently then? We all know it's going to have a lot more events. So we're looking at greater than 10 times more transient events per year. So this is just showing the timeline. So this is stolen from Mika. It's a little bit old now, but you can see that there's this ramp up, and then I don't know why LSST was a question mark. I'm pretty sure it was happening back in 2020. But we're now going to be looking at 10 times more transients every year. So currently we're on about 20,000 extragalactic supernova-like transients are discovered each year. We classify about 10% of those, less than 10% of those. And so we're just moving into a whole other era now in LSST, as you're all aware. Okay, so then I can't talk about everything in supernovae and transients, so I just wanted to focus on a couple of different aspects that I think will be particularly relevant for LSST. So one is mapping this diversity of the transient universe, which I'll explain more about in a minute, and the origin of the elements. So where do heavy elements come from? How can we constrain the relative rates from different types of transients? And then finally, the dark energy constraints. So what are the key things that we need in terms of ESO follow-up for this? So starting with mapping the diversity of transients. So this is a similar one of these peak luminosity plots, so brighter up here, fainter, and then a characteristic timescale, so some timescale for how fast it evolves. And so you have normal core collapse supernovae in this box here, you have luminous red novae, you have superluminous supernovae, and then you kind of move into the more unusual classes where we have much lower numbers of them. And so as we all know, one of the key things with LSST is designing a cadence that makes as many people as happy as possible, but not everyone will be perfectly happy. And so this is Federico Bianco's, so this is from 2022. This is just a rolling cadence example. So you can see here the different bands from U to Y. And so this just shows the typical time scale between repeat visits to the field. So at any field, it's going back somewhere like 3 3.5 days to that particular field, but it's not in the same color. So that does introduce additional challenges then for detections of transients. It also means that some of these faster transients, which I'll discuss in a minute, are made much more difficult to discover and follow up. However, in a positive note, I think LSST will be really good straight off for very bright, very long-lived transients. So I call these long-lived brighter things, so the super luminous supernovae. It's going to be really good for these. So these are events that appear much brighter than normal transients, and a key question is trying to understand where does this extra luminosity come from. And so there are a couple of different models that have been put forward. Magnetars are one of the key ways that we think a lot of them are. So a magnetar forms when the star collapses, and then it's the additional luminosity from this that powers this brighter light curve. Some of them show circumstellar interaction signatures, so we think that's some kind of interaction in those. And then there's also models suggesting parent stability supernovae. So these will be exciting to study, but I don't think there's that many very good cases. And so the typical numbers now we're looking at is about 10,000 superluminous supernovae out to a redshift of 3 are the predictions in LSST. And so these should have great light curves for studying populations of, they're going to be quite easy, I think, to identify. We can get spectra probably out to about a redshift of 1 with some of the 10-meter class telescopes. And so that's going to be very nice. Similarly, for some of the longer-lived tidal disruption events, there's predictions of up to 80,000 TDEs in the LSST lifetime. So this just shows some of the model light curves. So because these extend over many hundreds of days, they should be relatively easy to find out to quite high redshift. So I think these longer-lived transients, I think, have really exciting science that's going to come out of LSST quite naturally. I think on the faster timescale, it is going to be trickier because of this cadence issue. And if we want to go down, to transients, we don't really know what's here, but what varies on a day timescale, or kilonovae, which we know are fast and faint evolving. And this is going to be a lot trickier. Again, just because of this cadence issue, because if we're not going back quickly enough, we can't find them quickly enough. And so this is one of the things I think when we're discussing like rapid TOOs with ELT, I think it's this issue, it's going through the brokers and actually identifying interesting things that we would then be confident enough to trigger ELT on, is going to be one of the challenges. And so I definitely think as well, there's really a role for low or smaller telescopes to do low redshift, higher cadence surveys. And so there are many of these that are planned, are ongoing. So Black Gem Atlas and the Lucia Southern Sky Survey, which is on the, if people know the old Lucia Quest survey telescope. And so it should be starting hopefully late in this year, maybe early 2025. And so it's going to do low redshift observations to get higher cadence. And so I think some way of combining this with the LSST alerts is going to be really powerful. Okay, so then in terms of follow-up, so Isabel's going to give a talk on Foremost on Thursday, but just, I guess, to show this nice video before she gets a chance to. So this is, so Foremost is a multi-object spectrograph going on the Vista telescope. And these are some of the little fiber positioners inside it. So it's got 2,500 fibers. And so each of these will be able to take a spectrum at the same time in a 4 square degree field of view. And this just shows the little positioners that are now, this is a prototype, that are working and are able to be put on a particular target. So we can submit target catalogs and then get our spectra back. And so the idea for this is that we're not going to point Foremost at any particular area of the sky. We're just going to naturally pick up the transients that LSST has found. And so this shows, this is from Chris Frommeyer. So for an LSST baseline 1.7 survey, so you can see LSST are these different colors from blue to yellow, determining how many days past observation. And then the red diamonds are the Foremost observations. And so you can see that it just, when Foremost observes, there will be LSST transients in that field, and then we'll observe those. And so we estimate there's probably about 12 live transients in every Foremost pointing, and we'll put a fiver on each of those. So we're talking a few hundred a night of transients with foremost. And so that means then over the lifetime of foremost, so in 5 years, we expect about 35,000 transients. So this shows the numbers as a function of redshift. Now this is dependent on the final exposure times and different estimates of the rates. But we're looking at, we can get type 1As out to a redshift of about 0.6. The solid and dashed are two different signal to noise ratio calculations. But even conservatively, it's about 35,000 transients over 5 years. Because we can't point it though, I think there's really still a lot of space for ELT, VLT and SOX to do targeted observations. We're hoping to get onto the foremost. So what we want to try and do is shorten the time between LSST visiting a field and then foremost observing that field as well. So we have to try and adjust the scheduler. But then at late times, we will need larger facilities to go back and try and get more detailed physics from these supernovae. Okay, so then one of the other questions we want to try and look at is the origin of the elements. And if LSST is perfect for trying to do big, global, universal style surveys to get rates of transients, because we're going to be able to get very deep, and so we'll be able to probe a very large volume to get down the uncertainties on this. But then the other thing, if you think about it, if you want to study what are the rates of elements that are produced per event, you need to know how much of, say, iron is produced in a type 1A supernova. And the way you can do that is by modeling the late time spectra when you can see into the core. And so then you can get an estimate. And so it's similar for other types of transients. So like kilonovae, you need detailed spectral modeling. So for example, these kilonova spectra, again, you can do detailed modeling so you can identify strontium, and then you can get an estimate based on calculations of what this means for different elements that are produced. And so I think this is one of the key things that we want to do with kilonova observations. Similarly, for some of the faint classes of transients, so there's this class called the calcium strong. They're defined based on the fact that they have very strong calcium in their spectra at late times. But they sit below normal type 1As in some of the weirdo classes. So magnitudes about -14 to -16. We're not sure if some of them come from core collapse, some of them are from white dwarf explosions. They also have very unusual locations very far from their host galaxies. So we don't really know what's going on with them. But if we want to try and constrain the overall production of heavy elements in the universe, we need to be able to constrain the rates and how much of different elements are produced in these. Okay, and then excuse me, to discuss then the dark energy constraints with transients. As I said, the latest dark energy survey results have gone to photometric classification. I think there is still a space for spectroscopic training samples. This is one of the things that we want to do within Foremost. I know SOX is also looking at this, and at higher redshift with the ELT. So these are some simulated Foremost spectra at different redshifts. So you can see you got a beautiful spectrum at redshift 20, magnitude of 20, and then in the R band at a 23rd magnitude, you can see the signal to noise is very low. And then you can debate whether you could actually classify that as a type 1A supernova. I think some people would say yes. And then you can also go to higher redshift. So with Harmony on the ELT, this is a simulated spectrum in a 3-hour exposure at a redshift of 3. So you're shifted into the near infrared. And again, hopefully you'll be able to classify that and use it in your training samples for your photometric only classifications. The multi-object spectrographs can also get huge numbers of host galaxies. So at the moment, this is key for the supernova cosmology. We'll get about 50,000 host redshifts with Foremost. Isabel will talk more about that. But then we can also do standard cosmology as well. We'll have about 20,000 normal type 1A supernovae. So we can do with spectroscopically classified out to a redshift of 0.6. Okay. So then these are the kind of main science questions. There are many, many more that we can try and understand on binary star evolution and mass loss and all these different things that do require different observations very early after explosion or at very late times. And so they require different capabilities. I think the photometric classifiers and the anomaly detection software in the brokers is going to be essential if we're going to weed out the interesting things, particularly if we want to trigger larger facilities. You need to be reasonably confident that what you're going to trigger is an interesting target. And we won't have the opportunity with these fainter events to get something in a different telescope first to confirm it. I think it's highly desirable if we can bring in other wavelength data from other wavelengths into the brokers, and also combining these high cadence surveys. So LSST won't be good, it'll saturate for the very low redshift events. And so I think we do want to bring in, say, Black Gem or Atlas or LS4. We want to be able to combine that data so we can study these nearby events. And also multi-wavelengths. So I haven't spoken about high energy triggers, but I think if we had the way to combine this, that would be very desirable. Then I think we have to move to multiplexing with foremost or WST in the future. This is the only way we're going to get a reasonable percentage, whatever that means, of LSST transients. But we really want to take advantage of spectroscopy, I think, for a lot of the, maybe less so for the cosmology now, but much more from the transient astrophysics. I think we still do need the spectra if we want to understand them. And then for later time observations, when the objects are fainter, but we can get a handle on the nucleosynthesis, we're going to have to use VLT, potentially in some kind of larger survey type operational strategy. I think this could be key. This could be one way around not having information on what type of transient it is to start with, and not needing a very specific science case, as some of the people were discussing earlier. This kind of gives a broader scope for classification and follow-up. Okay, that's the end. Thank you very much.
Do we have questions? Okay, now I see several hands. I think you were first.
Hi, thanks for a great talk. You mentioned 12 transients in each field of foremost, right?
Yes.
How is that calculated? Is it 12 transients